Imagine a room that stays cool even in the heat of summer, without any air conditioners or cooling machines. Or imagine clothes that make you feel cooler than if you were wearing nothing at all. Sounds like something out of a fairy tale, right? But in fact, this is more than realistic. Materials with the so-called thermoradiative effect are already being developed to make exactly this possible. For example, in the year 2016, a group led by Professor Shanhui Fan from Stanford University managed to cool a nanostructured material made of silver and silica by 42 degrees Celsius below ambient temperature using purely thermoradiative means. And although such outstanding results are so far achieved only in laboratories, some thermoradiative materials are already undergoing field tests, and some are close to entering the market. In the near future, we may very well be able to buy cooling paint or cooling clothing in a regular store. In today's video, we will talk about the thermoradiative effect, the physical principles behind it, the technologies that use these principles, and what has already been achieved, as well as what scientists hope to accomplish in the near future. As always, let us begin with the very basics. Any solid body heated to a temperature above absolute zero emits electromagnetic radiation. To be precise, all substances emit such radiation, but solid bodies have an interesting feature. Their thermal radiation depends only weakly on their chemical composition and other specific properties. The intensity of thermal radiation per unit surface area for solids is described by the Stefan-Boltzmann law, meaning it is proportional to the fourth power of the body's temperature. The spectral composition of this radiation follows Wien's law, according to which the wavelength at which the body emits the most energy is inversely proportional to its temperature. For example, for a solid body with a temperature of 30 degrees Celsius, that is, 303.15 Kelvin, the maximum will occur at a wavelength of 9.56 micrometers. This corresponds to deep infrared radiation, and such radiation is invisible to the naked eye. However, if the body is heated to about 550 degrees Celsius, its emission shifts into the short wavelength region and often becomes visible. This is how heated metal glows red, and as the temperature increases, the glow becomes orange and then yellow. It is important to understand that a heated body emits radiation at other wavelengths as well, but the intensity of those wavelengths will be lower and will drop quickly as the distance from the peak increases. The result is that the body's spectrum looks roughly like this. And the most fascinating part is that this spectrum's shape almost does not depend on what specific object we are looking at. There are exceptions and subtleties, and those are exactly what we will focus on in this video. But let's not get ahead of ourselves. We will discuss in detail in one of our upcoming videos where thermal radiation comes from, why it is more or less the same for all solids, and why gases of different composition may radiate very differently. For now, let us state the main idea. The source of thermal radiation is the fact that the atoms and molecules of all substances, including solids, are constantly in thermal motion. They vibrate, rotate, and perform other kinds of motion. And since thermal motion is random, although governed by certain statistical laws, the radiation generated by it also has a statistical nature. From this, the formulas for the Stefan-Boltzmann and Wien laws are derived. Radiation carries energy away, so as a result of thermal radiation, the body cools down. For example, the power of thermal radiation from the human body is about 100 watts, or 100 joules per second. That is quite a lot. In 1 hour, the body radiates enough energy to boil 1 liter of water. And conversely, if we kept losing that much energy for 4 to 5 hours without replenishment, we would freeze to death. But that does not happen, in part because our body, like all other bodies, not only emits radiation, but also absorbs radiation from the surrounding environment, ultimately from other warm bodies. That means the temperature of any body is determined by the balance between emitted and absorbed electromagnetic radiation. For example, if a body emits more than it absorbs, it cools down, which according to the Stefan-Boltzmann law leads to a reduction in its radiation intensity. When the two processes balance, the body reaches thermal equilibrium with its surroundings. Conversely, if a body emits less than it absorbs, it heats up. and its radiation increases until emission and absorption reach balance at some specific temperature. Of course, radiation is not the only mechanism of heat transfer. There is also, for example, heat exchange with the surrounding environment, that is, the direct transfer of heat from one body to another. In air, for objects at room temperature, heat transfer by conduction and radiation occurs with roughly equal intensity. But for now, let us focus specifically on radiation. So in thermal equilibrium, a body emits exactly as much electromagnetic radiation as it absorbs. However, in a medium such as air, these processes occur somewhat differently for electromagnetic waves of different wavelengths. For instance, air poorly transmits infrared electromagnetic radiation with wavelengths from 5 to 8 and from 14 to 18 micrometers. This radiation is quickly absorbed and scattered by the air, which then heats up and re-emits the radiation back toward the source. Essentially, for infrared radiation in those wavelength ranges, air behaves almost like a blanket for heat exchange. The body does emit radiation, but it almost immediately receives the heat back again. It is a different matter for wavelengths between 8 and 14 micrometers. Atmospheric air absorbs almost none of this radiation, and it passes through the air nearly unimpeded, effectively carrying heat away into outer space. It is like when we stick a foot out from under the blanket when we get too hot. If our body wants to cool itself efficiently through radiation, it should emit as much energy as possible in the 8 to 14 micrometer range. Unfortunately, when it comes to radiation, sticking a foot out from under the blanket is not so easy. Because, as we already mentioned, the radiation spectrum of a solid body is determined by its temperature, according to Wien's law. Yes, the spectral maximum of thermal radiation for objects at room temperature, including the human body, lies around 9 to 10 micrometers, which is right in the center of the transparency window. But a significant part, nearly half, of the total emitted energy falls into the spectral regions that are blocked by the air blanket, and that energy effectively goes nowhere as it is quickly returned. The secret of thermoradiative cooling lies in modifying the emission spectrum so that more energy is emitted inside the transparency window and less, ideally almost none, outside of it. This is called selective thermal emission. If we succeed in doing this, we can create a material that cools more efficiently through radiation than an ordinary solid body, meaning it will reach thermal equilibrium with its environment at a lower temperature, and therefore will become colder than the surrounding air. But how can we achieve selective emission? To do that, we need a material that contains particles capable of oscillating at specific frequencies and, as a result of these oscillations, emitting electromagnetic waves of certain wavelengths. In our case, those that fall precisely within the transparency window. One such material, capable of selective thermal emission in the atmospheric transparency window, is barium sulfate, chemically barium SO4. In the crystal lattice of barium sulfate, barium ions are bonded to the oxygen atoms of the sulfate ion SO4 by covalent bonds, which behave somewhat like springs. If this structure is pushed from the outside, the sulfate ions begin to vibrate. The frequency of these vibrations turns out to be 33.3 terahertz, that is 3 times 10 to the power of 13 hertz. Oscillating at this frequency, the negatively charged sulfate ions emit electromagnetic radiation with a wavelength of exactly 9 micrometers. And this radiation passes through the transparency window extremely well. This does not mean that barium sulfate emits radiation only at the frequency of 33.3 terahertz. Its atoms, in addition to vibrating at their natural frequency, also participate in ordinary thermal motion. In other words, the molecules of barium sulfate and the atoms within them vibrate more or less randomly, but they do so less randomly than in other substances because they have a preferred vibration frequency. Vibrations far from this frequency are suppressed, while those close to it are enhanced, which leads to a redistribution of the spectral energy density of the emitted radiation. If for typical solid bodies at a temperature of, say, 300 Kelvin, about 40 to 50% of their thermal radiation falls within the transparency window, then for barium sulfate, it is around 98%. That is, almost all of its thermal radiation effectively works toward cooling the body. However, simply using barium sulfate for thermoradiative cooling under real-world conditions does not quite work. That is because in real conditions, a body absorbs not only thermal infrared radiation from the surrounding environment, but also radiation from other sources, the main one being the sun. Earlier, we mentioned that the power of thermal radiation, and likewise absorption, from 1 square meter of surface at a temperature of about 300 Kelvin is roughly 100 watts. Meanwhile, the power of incoming sunlight is about 1,000 watts, 10 times higher. If our body absorbed all that energy, we would literally be cooked alive in just a few seconds on a sunny day. Of course, that does not happen, partly because we do not absorb all of the solar radiation. We reflect some of it. Additionally, we are prevented from overheating by heat exchange with the surrounding air, including radiation, which removes part of the heat. And if we are talking about a human body or other living organisms, we must also consider other thermoregulation mechanisms, such as sweating and so on. But we will return to that a bit later. For now, what matters is this. In order to create a coating that passively cools the body beneath it, we must not only ensure selective emission of the body's own heat into the surrounding environment, but also make sure that this coating absorbs as little solar heat as possible. That is, it should reflect as much of the sunlight as it can. And here is where barium sulfate has a problem. It is a transparent material. It reflects about 5% of incoming sunlight, absorbs another 5%, converting it into heat, and allows the remaining 90% to pass through. Fortunately, we can significantly change the way barium sulfate interacts with sunlight if we use not a solid layer, but a suspension of microscopic crystals. In fact, we see how this works in everyday life. Sugar or salt crystals, which are transparent individually, appear white when poured into a jar. And many transparent ice crystals form white snow, capable of reflecting a significant portion of incoming light. Here's how it works. A beam of sunlight is partially reflected from the surface of a single crystal and partially refracted into it. The refracted rays reflect again from the internal surfaces of the crystal, then they hit other crystals, reflect and refract again. As a result, a large number of almost transparent crystals together behave as nearly opaque. Light cannot penetrate deeply into a layer of such a material. It scatters and exits. That is, we observe reflection of light by the substance, but not mirror reflection, rather a diffuse reflection due to many scattering events on the tiny crystals. This process is most effective when the sizes of the particles are approximately equal to the wavelength of the incoming light. This kind of scattering is called Mie scattering, named after the German physicist Gustav Mie, who first described the process in the early 20th century. So if we create a suspension of barium sulfate consisting of particles of different sizes that correspond to the spectrum of sunlight, we will get a material capable of reflecting sunlight very effectively, even if the particles themselves are transparent, like barium sulfate. In fact, we want the particles to be transparent because that means less light energy is absorbed as the light passes through them, which means the reflective layer will heat up less. So the drawback of barium sulfate becomes its advantage, in addition to the thermoradiative effect caused by selective thermal emission. It was exactly according to this recipe that, in the year 2021, a team of scientists from Purdue University in the United States created a cooling coating. The paint, named Purdue Ultra White, is made of barium sulfate particles with diameters ranging from 50 nanometers to 2 micrometers. This allows the material to effectively reflect a wide range of solar radiation, in total about 98.1% of incoming sunlight. Moreover, thanks to the selective emission of barium sulfate, 97.7% of the thermal radiation generated by this paint falls within the atmospheric transparency window. As a result, surfaces coated with Purdue Ultra White are 4 to 5 degrees cooler than other white surfaces during the day, and 2 to 4 degrees cooler at night. In other words, thermoradiative materials that provide cooling purely due to their optical properties already exist. However, Purdue Ultra White also has its drawbacks. For the coating to function properly, it needs to be applied in a relatively thick layer, up to 0.5 millimeter thick, which is quite a lot by the standards of modern paint coatings. In addition, this paint is relatively heavy. To achieve the necessary thermoradiative effect, About 700 grams of Purdue ultrawhite must be applied per square meter of surface. And the strength of the thermoradiative effect itself is not especially impressive for such parameters. One of the reasons for this is the following. Barium sulfate particles, while selective in terms of frequency and wavelength of emission, radiate equally in all directions. As a result, only about 15 to 20% of the radiation escapes into the environment. The rest is either reflected inward, heating the coated object, or trapped within the layer of paint, heating the paint itself, and thus what we painted with it. But what if we could make the particles radiate in a specific direction, for example, outward, like microscopic antennas? That would definitely increase the efficiency of thermoradiative cooling by several times. And the most exciting part is that methods for achieving directional selectivity, not just in frequency, but also in angle of emission, already exist. This effect is achieved using metamaterials, materials made of specially engineered microscopic particles with carefully chosen shapes and artificially controlled orientation in space. For example, microscopic flakes of hexagonal boron nitride are often used for this purpose. These flakes are placed on the surface of the material, and they truly are capable of emitting thermal radiation, not in all directions, but only in one, outward. A correct explanation of why this happens is fairly complex, but I will try to explain it in the simplest way possible. And as always, I hope that this simplification does not make the explanation entirely incorrect. Crystals of hexagonal boron nitride are structured as layered flakes. Each layer is a film made of boron and nitrogen atoms strongly bonded to one another by covalent bonds. But the layers themselves are held together only by much weaker van der Waals forces. As a result, the boron and nitrogen ions vibrate mainly within the plane of the layers, where strong elastic bonds exist, and barely vibrate in the direction perpendicular to the layers. And as we know, oscillating charged particles emit radiation in the direction perpendicular to the plane of their vibrations. That is, up and down, but not left or right. So the ions in flakes of hexagonal boron nitride do not just oscillate at a certain preferred frequency, like the ions in barium sulfate crystals. They also oscillate in a certain preferred direction. The result is a kind of double selectivity, by frequency and by direction of emission. And while in the case of barium sulfate, only about 1/6 of the total radiation escapes into space, in the case of hexagonal boron nitride, this fraction increases to 50 to 60%. And if the barium sulfate particles are backed with a layer of metal that has a high reflectivity for electromagnetic radiation, the efficiency can rise to nearly 100%. Unfortunately, for all of this to work, the flakes of hexagonal boron nitride need to have a width of about 1 micrometer, that is 1,000 nanometers. And it is not enough just to fabricate such flakes and place them into a material. They also need to be spatially oriented in a specific way. Achieving this alignment with such tiny particles is not easy, though some success has already been reported. The team behind Purdue ultrawhite paint is also working with this technology. In the year 2023, they presented a new version of their coating with added particles of hexagonal boron nitride. This not only increased the effectiveness of passive cooling from 4 to 5 degrees up to 5 to 6 degrees in the daytime version, but also improved the practical properties of the paint. To achieve the effect, it is enough to apply a layer with a thickness of up to 150 micrometers. What about cooling clothing? Work in that direction is also ongoing, and the principle is broadly the same. Selectively emitting particles, whether barium sulfate or hexagonal boron nitride, are embedded into fabric. To achieve the best effect, the fabric must both reflect sunlight well and freely let out infrared radiation emitted by the warm human body, as well as allow the passage of air and water vapor produced by sweat evaporation. In the year 2023, researchers from the University of Science and Technology of China presented a cooling fabric. The base of their material was cotton, into which microscopic particles of barium sulfate were embedded, along with calcium carbonate to enhance reflectivity. Even more promising are experiments with synthetic textiles based on nanostructured porous polyethylene. We have already learned how to make this material nearly completely transparent to infrared radiation by producing it from fibers only a few hundred nanometers thick. In clothing made from such fabrics, the wearer already feels noticeably cooler in daylight than in traditional fabrics like cotton or linen. And if selectively emitting nanoparticles are also embedded in the material, then an additional cooling effect can be achieved through thermoradiative emission. Experts expect that the first commercial samples of fabrics and coatings with passive thermoradiative cooling will appear on the market within the next few years, and widespread adoption could follow in the next 5 to 10 years. In short, the age of scientific achievements that seem almost like magic is inevitably approaching. On our channel, we will continue to follow its arrival by exploring the most promising technologies and the physical principles behind them. And if you enjoy what we do here on the channel, I invite you to become a sponsor, here on YouTube or on our Patreon or Boosty pages. Thank you to everyone who is already supporting the project, and to those who decide to join our community of sponsors today. All the best to you, dear friends, and see you again soon in our upcoming videos.